Hi there, and welcome to lecture 3 of Fox. We're going to be talking about making precise statements and, why. Just a quick recap of where we were. Last time we introduced the discrete objects, the fundamental objects that we're going to be talking about in this course, sets, sequences, and graphs. Again, then we introduced you to the notion of proof, where we emphasize the difference between an inductive proof, one based on data, which always leaves room for doubt. Maybe you didn't consider all the possible data, and then a deductive proof, which leaves no room for doubt. Ironclad, take it to the bank kind of proof. We discussed several examples of proofs. The dating game. We showed that nobody can meet more than 12 people. We discussed even squares. Okay, and a square is even only when it came from an even number, and even numbers are even squares. We talked about extremist parties, where you can guarantee, groups of mutual friends who can have a good time, or groups of mutual enemies who can have a war. Okay, and then lastly, we introduced the well-ordering principle, this fundamental axiom that is very important for discrete math. Ultimately, it will lead us to something called the principle of induction. In the last lecture, we used the well-ordering principle to show that the square root of 2 cannot be represented exactly as a rational number. There's no ratio of numbers that exactly equals the square root of 2. That's interesting, because it means that there are these other numbers, and we need to develop a theory for these other numbers. Okay, and those numbers turn out to be the reals. We won't say much about that, but proofs are very important in convincing us of statements. And once we have statements that are proved, you can take it to the bank, you can bet all your money on it, it'll never be false. Okay, not like an inductive proof. Okay, today's lecture, making precise statements. And we're going to talk about fundamental precise statements that you might like to make, and how you can combine, basic statements into more complicated statements called compound propositions. And lastly, we're going to introduce this concept of quantifiers, the ability to make statements about many things. Okay, so let's start with statements. Okay, 2 plus 2 equals 4. Well, that's a true statement. Nobody will say it's an ambiguous statement, and everyone agrees that it's true. 2 plus 2 equals 5. Okay, this is a false statement. Okay, but now let's distinguish a false statement from an ambiguous statement. So there's no ambiguity here. 2 plus 2 equals 5. We all understand what it's saying. It's just that it's false. Okay, you may have cake or ice cream. Now, there's an ambiguity here, which is, can you have both? So when Malik was going to birthday parties, the parent said, you can have cake or ice cream. Malik is greedy, he says, can I have both? What the parent actually means is, you can have cake or you can have ice cream, but you cannot have both. So actually, the parent means to say X or. And, a computer science parent at a party would say, you can have cake, X, or ice cream. Okay, but we need to pin down what we mean by or, so that there's no ambiguity here. The version of or that we will use in this class is that you can have cake or ice cream or both. Okay. If pigs can fly, then you get an A. Okay, now that's a fairly complicated sentence. There is no ambiguity here. Nevertheless, okay, to the uninitiated in propositional logic, which is basically the subject that we're talking about today, you might wonder, since pigs cannot fly, is it possible for me to get an A? Okay, and that's resulting from a common confusion regarding these kinds of if-then, what are called implication compound clauses, okay, compound propositions. Okay, now let's get back to this joke that we said, there is one soulmate for every person. Okay, now why is that a joke? It's a joke because there are two ways to interpret this sentence. Okay, the first is that there is a single soulmate who is the soulmate for everyone. So there's this busy soulmate, and everyone shares this soulmate. A second interpretation is that every person has their own special soulmate. Okay. Now, which did the girl mean? The girl meant 5B. And what did the boy interpret? The boy interpreted 5A. Okay. So, why do we care? Okay. Why do we care that this sentence can be interpreted in two different ways? And the reason we care is that we are interested in proof. And if you're going to prove something, you had better know exactly what it means. So let's think about what it would take to prove 5B. Okay? So we're going to ask, imagine the world is composed of only 6 people, A, B, C, D, E, F, our usual friends. Okay? And we're going to ask them who their soulmates are. So A says, Sue is my soulmate. B says, Joe. C says, Sue. So Sue is popular. Okay? D says that his soulmate is a red Porsche. Okay? So D is a peculiar guy. Okay? E says Sue. So Sue is really popular. And F says Sam. So what we observe from this is that every person does indeed have a soulmate. Okay? And so, 5b is essentially proved. Every person does indeed have their own special soulmate. But we have not proved 5a because it's not clear that one single soulmate is a soulmate for everyone, which is what we need to prove 5a. So you see that 5a is much harder to prove than 5b. Okay? And have we disproved 5a? We haven't even disproved 5a because it's possible that, for example, A also has Joe as a soulmate, and C also has Joe as a soulmate, and so does D, and so does E, and so does F. They might all have Joe as a soulmate. It's just that when you ask them, they gave you their maybe preferred soulmate. Okay? So we haven't disproved 5a either. So an interesting question is, how would you prove 5a? Okay, a proof might go like this. Well, after we made our first round of questions, we might have said, well, B, is Sue your soulmate? B says yes. Okay, C says yes. Okay, D says no. Okay, now we are stuck again. So Sue is clearly not a soulmate to everyone. So we go back to A. Do you have another soulmate? A says Joe. Okay, now B also has Joe. We might ask C, is Joe a soulmate? C says yes. Okay, we might ask D. D says yes. E says yes. F says yes. Okay, if all of them agree, then we found Joe as a single soulmate for everyone, and we've proved 5a, but not everyone might agree. Then we go back to A and ask for another soulmate, and this process goes on. It's very hard to prove 5a. And in mathematics, statements like 5a are equally hard to prove. Statements like 5b are equally easy to prove. Okay? And so it's very important to know what the meaning of a statement is precisely before we try to prove it. Okay, so let's get back to our propositions, and we usually use the letters P, Q, R, S, these little lowercase letters to represent propositions. It's a shorthand. So rather than always writing Porky the pig can fly, we might label it P. Okay, and it's pretty clear that the statement or the proposition Porky the pig can fly is false, so we say that P is false. Okay, we'll label the statement you got an A, so that's a well-defined statement, you got an A. It's either true or false. Okay, we'll label it Q, and we'd like to know, is it true or false? We don't know. Okay, Kilam is an American. That's another statement. Okay, we'll label it R. 4 squared is even. That's another statement. We'll label it S. R, which is Kilam is an American, could be true or false depending on who is Kilam. Okay, S, the statement 4 squared is even, that is true. Okay, because 4 squared is 16, which is even. Okay. So here are some basic statements, P, Q, R, and S. And what we're going to do, okay, so basic statements are easy. You look at it and you can analyze whether it's true or false. And this is a property of any basic statement. Any basic statement has to be true or false. Okay. Now, what we're going to do is we're going to study more complex statements. Okay. So we're going to combine these basic statements by using what are called logical connectors, and in combining these basic statements or basic propositions, we get what are called compound propositions or more complex statements. Okay, so let's start with our basic statements. P, Q, R, and S. Okay, and the first non-trivial thing we can do a statement is take what's called the negation or the not. Okay, so not. Okay, and in this case we're taking not of P. So this wedge-like symbol is the negation, not P. And okay, how do we read not P? So not the case that Porky the pig can fly. And that's exactly what we say. It's not the case that Porky the pig can fly. Okay. Okay. Next example of a connector, and. So, we have the symbol, this upside down wedge. So P and Q. Okay, so P and Q. So in this case, P is Porky the pig can fly, Q is you got an A, P and Q is the statement Porky the pig can fly, and you got an A. Okay. Let's talk about the OR connector. Okay. So OR, P or Q. So this wedge is the symbol for OR. And in this example, P or Q, Porky the pig can fly, or you got an A. Okay. So these are the fairly standard Boolean connectors that we are used to in Boolean logic. Okay, now comes the most sophisticated of the connectors, which is called the if-then. Okay, so the if-then connector, and we write, so what we would like to say is if P then Q, and we write P arrow Q. Okay, so that stands for if P then Q. We could sometimes read it as P implies Q. Okay. So if Porky the pig can fly, then you got an A. All I did there is substituted what are P and Q. So if Porky the pig can fly, then you got an A. So these are the four main connectors that we're gonna be using. Okay. These are examples of those four main connectors in action. Okay. And what we need to do now is we need to pin down exactly what those mean. Not and then or are going to be easy because you're familiar with them, and we're going to spend a lot of time on if then. Okay. Because we need to know exactly what if then means. We need to know what these connectors do to statements in getting compound statements. We need to know how the truth values of individual statements gets translated into the truth values of compound statements, because we want to prove things, and we'll want to understand if then very carefully, because most of the things that we will prove in this course involve if thens. Okay, so let's talk about compound propositions. Okay. And we have our original propositions, P, Q, R, and S. Porky the pig can fly, you got an A, Killam is an American, 4 squared is even. Okay. And now compound propositions are ways of combining these, as we already mentioned, to get more complex propositions. So let's start with not. Okay, so for example, not P. Okay, it's not the case. It's not the case that Porky can fly. Okay, very simple. Okay, so since Porky cannot fly, then P is false, and so not P is true. So not P is just the opposite of P. Okay, and if you're asked to prove not P, that amounts to showing that P is false. Okay, amounts to showing P is false. If you're asked to prove P, that amounts to showing that P is true. You're asked to show not P, amounts to showing that P is false. Okay, let's talk about and. Okay, so and P and Q. Okay, so Porky can fly, and you got an A. Okay, again, very simple. It's exactly what you're familiar with. Okay, P and Q is true. Okay, whenever both of P and Q themselves are true. Okay, so this must be true. This must be true. In order for the and to be true. Okay. Now, clearly, since Porky cannot fly, this is false, so the and is false. Okay. Anytime one of these are false, the and is false. So if you're asked to prove P and Q, okay, that amounts to showing P is true and showing Q is true. So you have to show both of these to show that P and Q is true. Okay? So that's exactly what we're familiar with. Okay. Or. Okay. So P or Q. Porky can fly, or you got an A. Okay, now the or is interesting. So it's not the common usage in the English language, which is the exclusive or. In math, we talk about the inclusive or. So the or will be true if either Porky the pig can fly is true. So if this is true, or if both are true. Okay. So it's easier to think about the situation where the or is false. The only case where the or is false is if both are false. Okay. And so if you're asked to prove P or Q, you essentially have to show that, it's not the case that both are false. Or equivalently, show that one of them is true. Show one of P/Q is true. Okay. And sometimes we resort to sort of interesting tricks, because sometimes it may not be obvious which one to pick to be true. So sometimes you argue as follows. Okay, P is either true or false. Okay, so let's consider the case where P is true. Well, if P is true, then the or is true. So let's now consider the case where P is false. If you can show that for the case where P is false, Q is true, then the OR is true. Okay, so that's sometimes we have to resort to sort of more subtle arguments. We'll as you become more familiar with proofs, we will talk about these kinds of things in greater detail. Okay, so that's the not, and or, and it's particularly useful to represent how when these guys are true in what's called a truth table. Okay, so if we have P, so we're dealing with propositions P, Q. Okay, so truth tables. Okay, so when constructing a truth table, you look at this complex compound proposition and what basic propositions does it involve, and you list out the basic propositions. In this case, P and Q. Okay, and you start by listing out all the possible truth values for this pair of propositions. So you can have false, false, you can have false, true, you can have true, false, and you can have true, true. As you can see, there are 4 possible truth values when you consider the pair, and I've listed them in a fairly systematic way. Okay, and now we talk about, let's say, not P. So what is the truth value of not P? Well, interestingly, not P doesn't care about Q, it only cares about P. So in this case, P is false, so not P is true, true. And in this case, P is true, so not P is false, false. Let's look at the AND. So P and Q, P and Q. Okay, so in this case, P is false and Q is false. So the AND, as long as one of them is false, that's all you need for the AND to be false. So false. Here this guy's false, so false. This guy's false, so false. The only case where the AND is true is when they're both true. Okay, and finally, let's look at the OR. Okay, and the only case where the OR is false is when both are false. So when both are false, it's false, and in all other cases, at least one of them is true, and so the OR is true. Okay, and so what we say is okay, I'll put a double line here. Okay, what we say, we've listed out the truth tables for not, negation, and OR. In some sense, the truth table captures the meaning of the sentence. When is it true? And if you want to prove that an AND is true, you need to prove that an OR is true, you need to prove that one of these 3 rows are the case in the truth table. Okay, now I'd like to talk about implication. It's the most complicated of these connectors. It's the most complicated compound proposition, and unfortunately it's also the most popular one when it comes to math. So most of the things that we like to prove involve the implication or the if-then. Now instead of talking about flying pigs and A's and so on and so forth, let's talk about a more down-to-earth implication. Okay, so if, and I'll put in brackets, it rained last night, so this is P, then the grass is wet. Okay, so this is Q. And this is an implication that we're all familiar with when it comes to everyday life, certainly, and so we believe that this is a true implication. Certainly, if it rained last night, the grass is wet. Okay, so let's try to pin down what it means. And so first, let's ask some questions. Okay, did it rain last night? Okay, don't know. Is the grass wet? Don't know. Okay, and so that's the interesting thing, is that we don't know anything. Okay, so then what's the purpose of this implication? The purpose of this implication is not that it tells us something new, is that it builds a link between 2 sentences. Okay. So it's building a link between raining last night and the grass being wet. Okay, and let me show you how we use this link. Okay, so you open up the papers. So in the papers, okay, the weather report says it rained last night. Okay, so now we have if it rained last night, the grass is wet, and I'm telling you it rained last night. So this says that P is true. Okay, so it rained last night. What do you conclude? Now we know something. Okay, now we know that the grass is wet. Conclude, the grass is wet. Okay, and we conclude that Q is true. Interesting. So that's one of the most important and most common ways in which we use this link that the implication gives us. Okay, so let me summarize it in sort of an algebraic way using these labels. So we know that P implies Q. So this is written P implies Q. So we know that P implies Q. That's true. Okay, and now when we opened up the papers, they told us that P is true. So P, that's true. Okay, and then we concluded. Okay, I'll use therefore. This is the symbol for therefore. I mean, you don't need to know all these things. I'm just, showing you some interesting things. Okay, therefore, we conclude. So what do we conclude? Q is true. Okay, interesting. Okay. So, if you have a true implication and you know the left-hand side is true, you conclude the right-hand side is true. Okay, now, instead of opening the papers, you went out. Okay. And you see that the grass is wet. Okay, so let's look at the version of this way. Instead of you find out that P is true, you find out that Q is true. Okay, so you went out and you find out that the grass is wet. So you find out that Q is true. Okay, so let's summarize algebraically what we know. We know that P implies Q, that's true. We know that Q is true. What can we conclude? Therefore. Okay. So I'm telling you that the grass is wet. Okay, so did it rain last night? Question mark. Okay, yes or no? And now you're thinking to yourself and saying, I'm not sure. And you're not sure because it may have rained last night, and that could explain the grass being wet, but it also may not have rained last night. In which case we might think, well, then what would explain the grass being wet? Well, maybe there are sprinklers that came on last night. Okay, so just because I told you that Q is true, that the grass is wet, you cannot immediately conclude without any doubt whatsoever that P is true. Okay, so what can we conclude about P? Nothing. It can be true or false. Okay, sad face. I don't know anything. Okay, so that's interesting. The sort of reversed version of this, where instead of telling you P is true, I tell you Q is true, does not let you infer anything about P. Okay? Okay, so this is the situation where P is true, where Q is true. Let's consider the situations where P is false and Q is false. So, you read the papers, and you find out it did not rain last night. Rain. And so this tells you that P is false. Okay, so let's summarize the situation. You know that P implies Q because from everyday reasoning, this is a statement that we believe is true. Okay, so you know that P implies Q is true. Okay, and now I'm telling you that P is false. It did not rain last night. So P is false. Okay, what do we conclude? Therefore, it did not rain last night. Is the grass wet? Is the grass wet? And the answer is, you stop and you think, I'm not so sure. Did not rain last night, so, it certainly sounds plausible that the grass is dry, but it's possible for the grass to be wet if the sprinklers came on. So we don't know. Okay, so Q, it can be true or false. So we cannot conclude that the grass is not wet. We cannot conclude that the grass is dry. Interesting. So if I tell you that the left-hand side is false, it does not necessarily mean that the right-hand side is false. Okay? And one last situation let's consider. So you went out, and the grass is bone dry. So the grass is bone dry. Okay? So this is telling you that Q is false. Okay? So let's summarize the situation. Okay, you've got that P implies Q. Well, we know that that's true. I'm telling you that Q is false. And so what does that allow you to conclude? Okay, so now let's think about it. Okay, we're asking you to conclude something about P. In other words, whether or not it rained last night. So, could it have rained last night? And here we can definitively answer no. Because we know that if it rained last night, the grass is for sure wet, so it cannot be bone dry. You're telling me it's bone dry, and so it could not have rained last night. Okay, well, if it could not have rained last night, then P is false. Okay, P is false. So therefore, P is false. Okay? Interesting. So I'm going to summarize this and I'm going to emphasize this. Okay? Summarize, emphasize. Okay? So when you have an implication that you know to be true, and that's the value of the implication, it builds a link between P and Q. Now if someone comes and tells you the left-hand side is true, you can conclude the right-hand side is true. Okay. If someone comes and tells you the right-hand side is true, you cannot conclude that the left-hand side is true. Okay. So the left-hand side can be true or false. If someone comes and tells you that the left-hand side is false, you cannot conclude that the right-hand side is false. Okay. The right-hand side can be true or false. If someone comes and tells you that the right-hand side is false, of a true implication, then you can conclude that the left-hand side is false. So in these two situations, you can make inferences. Interesting. Okay. But in these two situations, you cannot. Okay. So that's what we can do with a true implication. Now let's suppose we're trying to figure out whether or not this implication is true. Okay. Okay. So you're sitting down, you know, and you're reading the papers, okay, and you find out from the papers, you find out that it rained. So P is true. Okay, cool. It rained. Now, if this implication is true, okay, you're expecting the grass to be wet. So you go outside, okay, and you find out the grass is bone dry. Now remember, you know, one of the uses of the implication is that if I tell you that P is true, okay, for a true implication, if I tell you that P is true, you can infer, you can conclude that Q is true, but not that Q is true. But now you went outside and you find the grass is bone dry. Okay, so then something is wrong. Well, certainly it rained because everyone has verified that, and certainly you have verified the grass is bone dry. Okay, so the only thing that can be wrong, i.e., false, is the implication. Okay, so Q is false. Okay, this brings this implication, you know, under the microscope and says this implication cannot be true. Because if this implication is true, then Q must be true. We sort of argued that, we showed that, okay? So this is what we call a counterexample to the implication. This is what's called a counterexample to the implication. Okay? And if ever a counterexample appears, and even one counterexample suffices, so just one day in which it rained last night and the grass was bone dry. If one counterexample ever appears, then we conclude that the implication is false. Okay. So this means that the implication is false. Okay, so P implies Q is false. Okay. And that's the only way in which you can convince me that an implication is false. Find a counterexample. Okay. It's the only situation where an implication is false. So now, you know, I'm going to summarize our discussion in the truth table for implication. Okay. And that, in essence, pins down the meaning of implication. So let's go back to this truth table and add one more column for P implies Q. The only case where the implication is false is if P is true and Q is false. So here it's false. Everywhere else the implication is true. Okay. In other words, you know, we're saying that it is true. You know, what we mean is that any situation such as FF or FT or TT, those are consistent with the implication being true. You haven't shown me a counterexample which demonstrates the implication is false. So the truth table for implication, very simple. You know, the only situation where it's false is when P is true and Q is false. Okay. Now let's consider some implications that are not having to do with rain and grass. Okay. If n squared is even, then n is even. So this is P, this is Q, and we're saying P implies Q. Is this implication true or false? So let's see, is there a counterexample? So what would a counterexample look like? So n squared is even, that must be true. But we showed before that whenever n squared is even, n is even, so this must be true. In the situation where P is true, Q must be true. Okay, true, true, so this implication is true. Okay, let's consider another implication. So P implies Q over there. If Porky can fly, then you got an A. So we claimed this at the beginning of this lecture as an implication that would confuse many people who would argue as follows. Well, clearly Porky cannot fly, so this is false. So P is false. So therefore I cannot get an A. So therefore Q is false. But now remember back, when P is false, you cannot conclude that Q is false. That's one of the situations where you cannot infer. Okay. So, so this is false, and so, Q can be true or false. And this implication stays true, because look, when P is false, Q can be true or false, and the implication remains true. So this is a true implication, just by virtue of the fact that this guy, the left-hand side, is false. Because whenever the left-hand side is false, the implication is true no matter what Q is. And that corresponds to the fact that, you cannot pin down Q in any way. The implication remains true no matter what Q. Okay, so that's implication. Let me show you some additional uses of implication. Okay. So equivalence. So let's talk about equivalence. Another very important topic. Okay. So we say that P is equivalent to Q. Okay. What does that mean? What that means is that if you know the truth value of P, okay, so if you know this, then since they're equivalent, you know this. So what that means is that either they're both true, so if this is true, you know that this is true, or they're both false. So if this is false, you know that this is false. Okay. Okay. In the other situations, if it's possible for this to be true and that false, or this to be false and that true, then they're not equivalent. Okay, so P equivalent to Q, it would be false. Now we have a notation for this. We say that P is equivalent to Q. And I'll explain that notation very shortly. Okay, so let's see the truth table for P is equivalent to Q. So let me do another truth table here. P is equivalent to Q. So the equivalence is true if they are both false, the equivalence is true, or if they are both true, the equivalence is true. Okay. But the equivalence is false, so the equivalence is false when P and Q have different truth values. So there we have the truth table for equivalence. Okay. So let's look at this, a little more closely. Okay. So for the equivalence to be true, you cannot have P being true and Q being false. True, false is not allowed. So, P equals true and Q equals false is not allowed when P is equivalent to Q is true. Okay, because if If you have this row true, false, then the equivalence is false. Okay, but you know, if this is not allowed for a true equivalence, okay, if this row is not allowed for a true equivalence, that means that P implies Q will also be true. P implies Q will also be true. So in any true equivalence, P implies Q will also be true, because look, this is not allowed in a true equivalence. Okay? And if that is not allowed, then P implies Q is true. Okay, if that is not allowed, then P implies Q is true. Okay, now in a true equivalence, this second row is also not allowed. So P being false and Q being true, P equals false and Q equals true, is not allowed. Okay, so if P being true and P being false and Q being true is not allowed, okay, this means that Q implies P will also be true. Okay, because the situation where the left-hand side is true and the right-hand side is false is not allowed if the equivalence is true, and so Q being so therefore this implication will also be true. So let's see what we have. We have that P implies Q will be true. So whenever P implies Q, if and P equivalent to Q is true, then P implies Q is true, and Q implies P is also true. So both of these are true. If you write them on top of each other, you see these arrows become this double arrow. And so that's the origin of this notation with the double arrow for equivalence. Okay. So uses of equivalence. So one of the primary uses of equivalence, first, it establishes a tight link, even tighter than implication. Implication just says, so P implies Q just says that, whenever P is true, Q must be true. Okay. Equivalence says that whenever P is true, Q must be true, and whenever P is false, now in an implication, if you have false, Q could be true or false, but in an equivalence, whenever P is false, Q has to be false. Okay. So an implication is a tighter link. It says that both of these are essentially the same. Okay. So it establishes a tight link, even tighter than implication. It's very useful in definitions. Okay. And sometimes, instead of equivalent, we say if and only if. So sometimes we say P if and only if Q. Okay. And, whenever one is true, the other is true. Okay. So, let me give you some examples of definitions. U.S. citizen. If and only if you are born in the USA. Okay. So, definition. Now, whenever someone states a definition, you can't really argue with them. They're basically telling you that this concept, U.S. citizen, and this concept, born in the USA, are the same. If this is true, that is true. If this is false, that is false. Okay. If you're not born in the USA, let's say you're born in Mexico, you're not a U.S. citizen. Okay. So now when we look at this definition, we say, well, you're perfectly fine to define whatever you want, but that's not the definition of U.S. citizen that the U.S. government uses. Okay. So people are free to define whatever they want. Okay. It just establishes a link between two concepts. So let me show you a definition that, is more useful. Parallel. So two lines are parallel. If and only if, okay, the lines when extended infinitely in both directions do not cross. So this is the predominant use of a definition. So this concept of lines when extended in both directions do not cross is a very useful concept in mathematics and geometry. Okay, but now whenever we want to use it, we would have to spell out this whole thing. Okay, that's very inconvenient. Okay, so what we say is that we define parallel to be equivalent to that, and so now we say, instead of saying all of this, we just say, suppose the two lines are parallel. Now, why do we need this, this complicated definition? So it establishes, you might be wondering, why do I need this? Why don't I just say two lines that don't cross? Okay, well, these two lines don't cross. They're not parallel. Okay, but when you extend them infinitely in both directions, now they do cross. Okay, so parallel, we want to reserve this strong notion of parallel for example, these two lines. They are parallel. What that means is when you extend, they don't cross. It's a very sophisticated concept. Okay, and we define the word parallel to be equivalent to that concept. So if this is true of two lines, they are parallel. If this is false of two lines, they're not parallel. Equivalent concepts. Very useful in definitions. Now, don't just define things for the sake of defining things. Define things that are useful and make proofs and discussions, easier to understand, not harder to understand. Now, in this case, if you had a discussion which involves this statement, it would be complicated to follow. But everyone knows what parallel is, makes the discussion simpler. Okay? So that is equivalence. Okay, when it comes to implication, order matters. Okay, so now what I'm going to do is I'm going to extend this truth table. Okay, with a bunch of other formulae, with a bunch of other compound propositions that involve P and Q. And let's just play along for the moment. So, not Q implies not P. P, not P, or Q. Okay? So let's look at these two truth tables. Okay. So not P implies not Q would only be false when not Q is true and not P is false. So not Q is true when Q is false. So Q is false. Okay, and not P is false when P is true. So Q is false, P is true. So only in this situation is this implication false. Okay, so this is false. Everywhere else it's true. Okay, what about not P or Q? Okay, so not P or Q. Well, remember the or. It's only false in one situation, where both of these are false. So Q must be false and not P must be false, which means P must be true. P must be true, Q must be false. Okay, so this is the only situation where the or is false. In all other situations, the or is true. Okay, now I'm going to ask you to compare, okay, and I'll put a nice blue line here. Compare the implication with this, what's called the contrapositive of an implication, with this or. You will observe that whenever this is true, that's true. Whenever this is true, that's true. Whenever this is false, that's false. Whenever this is true, that's true. True, 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 true. False, false, false. So, whatever the truth value of this is the same as the truth value of that. So, these are equivalent. Remember, that's what equivalent meant. It meant that whatever the truth value, if P is true, Q must, if one thing is true, the other thing is true. If one thing is false, the other thing is false. So it's possible for compound statements to be equivalent. Okay, and we can evaluate the truth value of compound statements. Okay, let's consider one more example, okay, which is Q implies P. Okay, so Q implies P. Okay, so P implies Q, Q implies P. Well, when is this false? It's false when the left-hand side is true and the right-hand side is false. So the left-hand side is true, the right-hand side is false. So it's only in this row that it's false. Okay, it's true, it's true, it's true. Okay. And you can see that if you take the AND of this and this, so the AND requires both to be true. So both are true here, both are true here, and in this case, one of them is false. So the AND of this and this is exactly the truth table of equivalence. So equivalence is equivalent to the AND of P implies Q and Q implies P. Okay, so that's a small side note. What's the big side note? Q implies P does not have the same truth table as P implies Q. See? True, 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 false, false, true. So when one is true, it's not necessarily the case that the other is true. When one is false, it's not necessarily the case the other is false. Okay. So P implies Q is not equivalent to Q implies P. The order matters. Okay. And that's very important. Okay. If I'm dead, then my eyes are closed. This is true. It's a true implication. If I'm dead, my eyes are closed. Okay. If my eyes are closed, then I'm dead. You see the difference? All I did is change the order. Very different statements. Okay. The order matters a lot when it comes to implication. So if my eyes are closed, please don't conclude I'm dead and bury me. Okay. Please don't conclude I'm dead and bury me. The order matters when it comes to implication. Okay. All right, let's consider an example, a slightly more complex example. So example. Okay. So let's define some statements. P. Okay. You are hungry. Q. You are thirsty. R. You visit the cafe. Or if you're in school, you visit the cafeteria. Okay. So if you're hungry or thirsty, so if, hungry or thirsty, then, you visit cafe. It's a reasonable implication. It's certainly plausible. We might think it's true. Okay, so let's just assume it's true. What this means is that this means that P or Q implies you visit the cafe R. That's now an even more complex compound statement. Okay, so let me ask some questions. Okay. You are thirsty. Okay, pop quiz. You are thirsty. Did you visit the cafe? Did you visit the cafe? These are the kinds of questions we used to get on the GRE analytical, or what are called logic questions. Okay. 1. 2. You did visit the cafe. Are you thirsty? Question. Answer it. Question 3. You did not visit the cafe. Are you hungry? Answer it. Okay. So now let's pause the video, answer these questions. I'll give you 2 seconds. So if you pause the video and answer these questions, you're an excellent answerer of logic questions. But what I want to show you is that we can use truth tables and the basic propositional sort of logic that we have defined here to answer these questions effortlessly. Okay, so you are thirsty. So what that says is P or Q is true because P is true. Because Q is true. Q is true. So P or Q is true. Since P or Q is true, okay, and this is a true implication, we know that true, you can infer R. So you can infer that you visited the cafe. Yes. Okay. You did not visit the cafe. So R is false. Okay, so R is false. Okay, so are you thirsty? So we know that if R is false, okay, it cannot be the case. So we know that when we have the right side of an implication is false, we can infer that the left side of the implication is false, because it's a true implication. So this is false. But when is the or false? When both are false. So this is false, so this must be false. Both must be false. So you are not thirsty, you are not hungry. So are you hungry? No. Oh, I was talking about this. Are you hungry? No. So you did not visit the cafe. You did visit the cafe. So R is true. Okay. When you did visit the cafe, R is true. So if R is true, well, in an implication, we studied this case. When R is true, you cannot conclude anything about this. This can be true or false. And since you cannot conclude anything about this, you cannot conclude anything about what's inside. So this can be true or false, which means P, are you thirsty, which means Q can be true or false. Okay, if Q is true, this is true. If Q is false, this could be either true or false, and you cannot infer anything. So don't know. There's an important difference there. We don't know. We know that Q must be true or false, but we don't know. So you did not visit the cafe. Oh, sorry, you did visit the cafe. You might have just been accompanying a friend. You may not be hungry or thirsty. So just because you visited the cafe doesn't mean you're hungry or thirsty. That's not contained in the implication. Okay. So work through this example, carefully on your own. It's a very important example, okay, to understand implications. I want to move on. Okay. To quantifiers. So quantifiers. Okay. Essentially, we're now moving towards that complex statement. Okay. There is a soulmate for every person. Okay, and remember there were two versions of this. Version A was there's one soulmate who's the soulmate for everyone, that busy soulmate. And version B, that every person has their own individual soulmate. Okay. Now, I want to emphasize that this is a complicated sentence. It's a complicated proposition. Okay? And that has to do with the existence of what we call quantifiers. So let me underline the quantifiers. Okay, so in this case, let me sort of, there is A. So it's a quantifier. It's telling you how much of something, we're talking about. And for every person. Again, it's telling you how much of something. So it's for all the people. Okay, let me show you some similar sentences. Okay. Kilam has some gray hair. Okay, so here's the quantifier, some. It's telling you about how many. Okay, quantifier. Quantifier quantifies. Okay. Any map is 4 colorable. That means that you can color the map so that you assign countries with colors, you assign colors to countries, and no 2 adjacent countries have the same color. So we say that any map is 4 colorable. Here's the quantifier. It's telling you how many of the maps are 4 colorable. Basically, it's saying all. Okay. So this is sometimes called the 4-color theorem. It was only recently proved when you talk about the context of the history of mathematics, recently proved. Okay. Every n, so every integer n that's greater than 2 is a sum of two primes. This is what's known as Goldbach's conjecture. Okay, so where's the quantifier here? So every, it's talking about how many numbers bigger than 2, and in this, it's a very large number. We're saying all of them. Okay. You know, someone broke this faucet. Okay, where's the quantifier? Someone. Okay, it's telling you about how many, one person. Okay. There is a creature with blue eyes and blonde hair. Okay. These are all perfectly valid English statements, and they are complicated because of this quantifier. Let's finally end up with one that will be easy for us to sort of get to grips with. All cars have 4 wheels. Okay. Boom. Whereas the quantifier all, telling us something about how many, quantifying. Okay. So we're going to come to grips with this guy, and eventually we're going to end up, you know, figuring out what's going on with that guy. Okay, so quantifiers. Okay, so all cars have 4 wheels. What are we really saying? Okay, so let's define the set of all cars. So the set of cars, C. Remember our way of defining sets? So the set of cars, C, is a set. Okay, and I'll use C to represent, little c to represent a generic car, where little c is a car. Pretty trivial definition of the set of cars. It's just that I've defined a set, and to belong to this set, you must be a car. Okay. Now, in order to make this statement sort of mathematical, we're going to introduce the concept of a predicate. Don't worry, nothing complicated here that you haven't seen before, but you may not have seen it in this way. So you've all seen the concept of a function. So f of x equals x squared. What does this do? It says that, you know, give me a value x as input, and I will output x squared. So we could say something like f of 2. So f of 2 is equal to 2 squared, which is 4. Okay. We've all seen the concept of a function. Well, a predicate is basically a function. Now, when you have a function, you have an input and an output. And functions are very convenient and familiar to us because the input and output are both values. But technically speaking, you know, when we formally define functions, we say there's a domain and a range and so on and so forth. Okay? So a predicate is exactly that. Okay? It's a function. We call it a predicate, but it's a function. Okay? The input is a member of some set. Now, just like functions, a predicate can have more than one input. So a function can have more than one input. You know, a function of x and y. So a predicate could take as input, you know, 2 objects, a member from set 1 and a member from set 2. Okay? But for the moment, let's consider a simple function. The input is a member from some set. So for example, this set. Okay. The output, now this is where the predicate becomes kind of unfamiliar. Okay. The output is a statement. Okay. It's not a value, it's a statement. Okay. And if I'm being perfectly meticulous, here's an example. I'm going to define the predicate just like I defined f of x. I'm going to define the predicate p of c. Now remember what c is? C is a generic representative of an object from the set of cars. So this tells you that this predicate takes as input a car, which I'm generically calling C, and the output is a statement. Car C has 4 wheels. So for example, I can, just like I can compute f of 2, I can compute p of, you know, of Malik's Ford Escort. So that's a perfectly valid input because it's the label of a car. It's a car. So the output would be car, Malik's Ford Escort, has 4 wheels. Okay. Now that's a very bizarre statement. It's a very bizarre sentence, but if you think about it, it's perfectly correct. You know, the car labeled Malik's Ford Escort has 4 wheels. Now in English, we usually just say Malik's Ford Escort has 4 wheels. Okay, but when we formulate it in this fancy way with a function that takes an input and outputs a statement, we have to stick to the format for the output. And the output has this format. So that's the sentence, that's output. A bizarre sentence, but perfectly okay. Okay, now, all cars have 4 wheels. Okay, one way to say that is, for every car C that's in the set big C, so for every car C that's in the set big C, okay, now we'll use colons to sort of abbreviate, it is the case that. Okay, it is the case that, and we're going to assert P of C. And in parentheses, you can think of this as saying P of C is true. So we're asserting P of C. For every car C in the set of cars, it is the case that car C has 4 wheels, because that's exactly what this sentence is. This is equivalent to this. Okay, so mathematical version. Not a big deal. So we've just taken this sentence and given a mathematical way of formulating it. That's what we have done. Well, we're going to get more fancy. Okay, we don't like to say for every car. Okay, so we have a symbol for that. For every, that's called the for all. So we just say for all C. So this upside down A is a shorthand for all. So, okay, so let me translate this now. For all cars C in C. So the for all came from here. Okay, this guy is there. Okay, it is the case that, okay, so it is the case that came from here. Car C has 4 wheels. Okay, and that's P of C. So you see, this is a very long-winded way of saying exactly that. So for all cars, it is the case that car C has 4 wheels. That's exactly that. Okay, and this is just a notation that captures this. So the for all symbol, you say, you know, what set are you talking about? So your variable belongs to what set? Okay, and then you assert the claim you want to assert. So that's an example. All cars have 4 wheels. Another example. There exists, there is a creature with blonde hair and blue eyes. So let me define the set of creatures. A is the set little a where A is a creature. Okay, and I'll define a predicate, a function, just as I did before. So a predicate that takes as input A, okay, is returning the statement, you know, A has blonde hair and blue eyes. So that's the statement returned by P of A. And now what is this saying? Okay, this is saying there is, so there, sometimes we say there exists, so there exists is the same as there is. There exists a creature A in the set of all creatures for which or such that that creature A has blonde hair and blue eyes, so for which we're going to assert P of A. Okay. So here's a formal way of making exactly that claim. Okay. and we shorten this there exists a creature, so a creature A to a backwards E. There exists an A in, so this is there exists, backwards E, there exists a creature A in the set of all creatures for which we are asserting that P of A is true. Here, look at this complex English sentence, the same English sentence written in math speak, okay, using predicates and quantifiers. And the for all and the there exists quantifiers are the most common ones that we will use in this course. Okay, let me just show you that, you know, there are sometimes multiple ways to say the same thing depending on how you define your predicates. Okay. So here, let me define the predicate Q of A, not to confuse with P. A has blonde hair. So I'm simplifying the predicate. A has blonde hair. And R of A is the statement A has blue eyes. Okay. Then observe that I can make a compound predicate. So Q of A and R of A, because this is a statement and this is a statement, so I can take the and of a statement. So this is exactly the statement, A has blonde hair and A has blue eyes, which is exactly, you know, has blonde hair and blue eyes. Okay. So I can now rewrite this as there exists a creature in the set of creatures for which, or such that, I assert Q of A and R of A to be true. So you can have compound predicates. No big deal. So, you know, we are free to define predicates however we want, just as we're free to define functions however we want. The only question is whether the predicate is useful and what is the set that is involved in, you know, invoking some statement about the predicate. Okay, this is a quantifier. Okay. Now, suppose it's not the case that all cars have four wheels. So it's not the case that all cars have four wheels. So there are certainly some three-wheelers in the country there that I was born. So it's not the case that all cars have four wheels. So this would be, it's not the case that negation, so you can negate statements involving quantifiers. It's not the case that for all cars in the set of cars, you know, I can assert P of C, where P is the claim, you know, car C has four wheels. P of C is the claim car C has four wheels. So now let's think about this. What is this saying? If it's not the case that all cars have four wheels, it means that some car does not have four wheels. So there is a car that does not have four wheels. Okay, so this is, there exists a car in the set of cars C. So there exists a car for which, such that the car does not have four wheels. What does that mean? That means that I can assert the negation of P of C, such that the negation of P of C is true. So I can assert the negation of P of C. It's not the case that car C has four wheels. Okay? So when we think about these two statements, we realize that these are exactly the same. So it means that this statement and this statement are exactly the same. Okay? They are exactly the same statement. And now let's do some pattern recognition. We see that in order to get from here to here, okay, I took the negation all the way into the P, into the predicate. So I said that, you know, the negation of this for all became, you know, a negation of the predicate, but providing that I flip the for all to a there exists. So you can move the negation across to the predicate if you flip the for all to a there exists. Okay? And let's consider the situation where there exists a creature with blonde hair. There exists a creature with blonde hair. Okay, so we said there exists a creature A in the set of creatures such that, A has blonde hair. So let's call that Q of A, the predicate. Creature A has blonde hair. Now supposing it's not true. So it's not the case that there's a creature with blonde hair. So it's not the case that there exists a creature with blonde hair. Now let's think about, okay, what does that mean? It's not the case. If it's not the case that there is a creature with blonde hair, it means that every creature does not have blonde hair. Every creature does not have blonde hair. Well, let's try to put this in math speak. So every creature, so for all creatures A that are in the set of creatures, we can assert that it does not have blonde hair. So we can assert that Q of A is false. So we can assert the negation of Q of A. Okay. Observe. We took the negation of a there exists statement and we converted it to a for all statement, but providing that we take the negation all the way to the predicate. So you can take the negation of a quantified exists statement all the way to the predicate, providing you flip the exists to the for all. That's the same thing that happened before. Okay? So negation, rule. You can take negation to the predicate by flipping the quantifier. So by flipping we mean for all becomes there exists and there exists becomes for all. Okay. So, just some practice with quantifiers. Okay. Let's talk about there is a soulmate for every person. So we're going to have to define some, predicates. And this is an example where we will define a predicate, i.e. a function. So let's define a predicate soulmate S, which takes as input two people, A and B. Okay? And we'll use this to return the statement, A has as soulmate, so person A has as soulmate person B. Basically, it's a very long-winded way of saying B is a soulmate for A. Okay. So we're clearly talking about people, so we could define the set of people. Okay, so the set of people, A, let's call it B. What can we use for people? Let's call people, I don't know, W is the set of people. So it's, the set of objects which I will generically refer to as W. Little w, W is a person. So I've defined a set. Okay, now, first version of that, okay, says there is one special soulmate. There is one special hardworking, I'll put special hardworking in parentheses. Okay, so there's one, just to imply that, that's not actually in the statement, but, that's what we really mean, that there's this hardworking soulmate who, such that that person is a soulmate to everyone. Okay. So what does that mean? That means that there exists. So there exists a special hardworking soulmate. So there exists a special hardworking soulmate B, okay, in the set of people, okay, such that, okay, that person B, okay, so B, that person, this person is B, is a soulmate to everyone. So what does that mean? Is a soulmate to everyone. That means that so this person B is a soulmate for all people A in the set of people. Okay, is a soulmate to everyone, i.e., so for all people A in the set of people. Okay. So for all people A in the set of people, this person is a soulmate to that person A. So for all A in the set of people, it is the case that B is a soulmate to A. But that's exactly what this predicate does. It's the case that B is a soulmate to A. So there exists this special B such that for all people A in the set of people, B is a soulmate to A. Okay, so this sentence in the first interpretation has this fairly complicated representation in math. Now, very often, we just ignore the statement of the set we're talking about because it's obvious. So we will typically say there exists B such that, for all A, it is the case that S of A, B. So I'm just removing, the set W from this picture because it's obvious that we're talking about people. Okay. Let's look at the other interpretation. So what's the other interpretation? Okay. The other interpretation is that every person has their own soulmate. So every person has their own special soulmate. Okay, so what we're saying is that for every person, for all A, it is the case that that person A has a soulmate. So it is the case that there exists a soulmate, there exists a person B, for which B is a soulmate of A. So that's represented by the predicate, by saying we're going to assert the statement S of A, B. Okay, so let me read it. For all people A, so each person A, there exists a B such that B is a soulmate, person A has as soulmate person B. B is a soulmate of A. Okay. Now, you will observe that these two interpretations of that complex sentence look very similar. The only difference is in the ordering of the quantifiers. So in going from this very hard to prove statement to this much easier to prove statement, the only thing that changed is the order of the quantifiers. Okay, so this is an example of what we call a statement that has mixed quantifiers because it has both kinds of quantifiers. Whenever you have mixed quantifiers, okay, the order of quantifiers matters. Okay. And that's basically the end of this lecture. The next lecture is going to be about proofs. So I'm going to list some statements of a more mathematical flavor. So these are kind of English statements. I'm going to list some statements of a more mathematical flavor. And I want you to just think about what it takes or what would it take to convince you to prove these statements to you. Don't prove them. Just think about what it would take. Okay. And now that we have quantifiers, you'll see that these statements involve quantifiers. So 1, okay, for all numbers n which are greater than 2. So this is kind of saying what's the set of things we're talking about. We're talking about numbers greater than 2. So every number greater than 2, okay, satisfies the property that, so we can assert that if n is even, okay, then n is a sum of 2 primes. So this is a conjecture due to Goldbach. Please don't try to prove this conjecture. I just want you to think about what it would take to prove the conjecture, to convince you of this conjecture. Okay, 2. There exists A, B, and C. So a triple of numbers, A, B, and C. So I'm writing that this way. Okay, there exists a triple of numbers A, B, and C such that, so we could say that are in, okay, n, to indicate a triple, we would say n cubed. Okay, so there exists a triple of numbers A, B, C that's in the set n cubed. So it's n, this is an n, this is an n, this is an n. So it says n cubed, n. Okay, for which a squared plus b squared equals c squared. Think about what it takes to prove that to you. Okay. You might recognize that this is related to something that the great Pythagoras proved. Okay. 3. There does not exist a triple of numbers a, b, and c, okay, in n cubed such that a cubed plus b cubed is equal to c cubed. Okay. Think about what it would take to prove this to you. This is related to something that apparently Fermat claimed to have proved. And think about lastly, for all a, b, and c in n cubed, we are going to assert that a cubed plus b cubed is not equal to c cubed. What would it take to prove that to you? Okay, I also urge you to think about the relationship between 3 and 4. Okay, and I'll see you next lecture. But think about what it would take to prove these things to you.